looking at, we're continuing with trig ratios, okay, but these are with obtuse angles. So we're now looking at triangles or angles that are now rotating out of the 90-degree range, okay? On your handout, which I see two gentlemen don't even have it out here, so you might want to get on that.
I don't know if I have this one.
Okay, I will find it for you then.
Is it the Trig one?
Yeah, it's trig.
Same one we got.
Yeah. Okay, so we're on lesson, 2.2, okay, lesson 2.2, so the diagrams that you're seeing are in your note already, so you don't need to copy it down. So what this is talking about is, I always tell my students to sort of think about these as a clock, okay? The only difference is the arm on the clock is going counterclockwise instead of clockwise, okay? So what happens is, they're saying, based on your Cartesian plane, you have something called the initial arm. The initial arm is running along that x-axis. It's as if nothing has moved. But now, as soon as I grab this arm and move it in any direction, going clockwise or counterclockwise, but clockwise most often, it becomes the terminal arm. The terminal arm always starts at the vertex 0, 0, and then has an end point at somewhere, okay? So your terminal arm can start at 0, 0. It can start in on the x-axis, which is a non-standard form. You can have two terminal arms. The initial arm might not be on the x-axis. It might be higher, and then your terminal arm rotates from there. So that's not standard form, okay? The ones we're going to see are standard form. You're going to see standard form, okay? It's just so you know that there are different types of forms. The calibration is really off. Okay, so a positive angle is formed by a counterclockwise rotation from the terminal arm. So a positive angle, and hopefully you know this already just from rotations, you start at 0 degrees, 90 degrees, 180 degrees, 270, 360, right? So what they're saying is you start at your, you start from your terminal arm as it rotates is a positive angle, okay? And then we're talking about this. So this is our Cartesian plane, and this is what I just said. At the initial arm, it's 0, right? 0 degrees. As you rotate, you hit 90 degrees, 180, 270, and back up to 360. That full rotation is your 360-degree circle. Everyone agree? Okay, what they do is they call this quadrant 1, 2, 3, and 4. Quadrant 1 is always here because it is the quadrant in which x and y are both positive. So you might want to add this. We know that this is x, this is y. Now this is negative. Oh, I can't write today. This area is negative x, and this is negative y. So quadrant 1 is always the quadrant where x and y are both positive. And then again, you go counterclockwise. So quadrant 1, 2, 3, and 4. Okay, 1, 2, 3, and 4. Sounds good?
So quadrant 4 is positive.
Quadrant 4, the ratio ends up being positive because you have a negative. Oh, no, sorry, quadrant 3, because you have a negative and a negative, so they'll become positive. But quadrant 4, your y is still negative, right? Just your x happens to be positive. Sounds good? Okay. So, a related acute angle is the angle formed by the terminal arm of an angle in standard position in the x-axis. Okay, the related acute angle is always positive and lies on the 0 to 90. In this example, beta represents the acute angle for theta. Okay, it's a lot of words. That's a lot of words. All they're telling you is, when your terminal arm rotates, in no matter what position it's in, no matter what quadrant it's in, you can drop a vertical line to your x-axis, only your x-axis. And what this means is I can drop a line here, or here, or here, or here. Does everyone agree with that? As soon as I drop that line, does everyone see I have like right angle triangles now? Mm-hmm. So based on that information, well, here is a right angle triangle. This one's easy because I could use SOHCAHTOA, and beta is theta. They're the same thing because it's rotating just in that first quadrant. This one here, if I want to find angle theta, which is this here, I could use SOHCAHTOA to find beta and then subtract it from 180 degrees. Does everyone agree with that? So I could go 180 degrees, subtract beta, and that'll give me angle theta. Because I know that this angle I can calculate using a right angle triangle. I know that this entire thing is 180 degrees. So in order to figure out theta, I could just go 180, subtract that angle I found. Okay, you might want to write that little 180 minus beta, but we'll talk about it. This one here, right? Again, you're 0, 90, 180, and 270, 360. Did I just mess up my numbers?
No.
All of a sudden it sounded weird when I said it. Okay. This one here, I know that I have 180 degrees and then I add beta. Plus that angle would give me angle theta. Everyone agree with that? Because that beta, or that next angle, rotates a little farther than the 180. And then this one here, I'm going to actually go, well, angle theta is equal to 360 degrees, subtract beta. Okay? Because I have an entire rotation. If I subtract this little bit, then I will know what my angle is. Okay, I promise this is not as difficult as it looks right this second. It's a lot of like language, and then as soon as you start doing it, you're like, oh, this is nothing. It's the same as I was doing before. Okay, it's just all of a sudden on that Cartesian plane. Okay, so sine and cosine of angles greater than 90. So let's say you have a point, PX, in your first quadrant. Draw a terminal arm, and then construct a right triangle by drawing a vertical line from PX to the x-axis. Okay, so all this is saying, and you guys have this in there, in your diagram, right? So what this is saying is, I would have a line going from my vertex out to the point. Out to the point. This is my terminal arm. This is my terminal arm. We know in any case, I can drop a vertical line and it'll become a right angle triangle. Does everyone agree with me right now? Okay, now, so what they want us to do now is instead of using opposite, hypotenuse, and adjacent, we're now going to use x for the x-axis, y for the y-axis, and r for your hypotenuse. The reason r is your hypotenuse is if I ran this all the way around in a circle, wouldn't my terminal arm be my radius of the circle? So what happens here is my hypotenuse is r, because that is the radius of my circle. Again, it's like a clock. If I moved that arm around in a circle, it would create that circle, and that would be from the middle point to the outside, right? We know, I'm just going to write this here, that this is x, this is y, this is negative x, this is negative y. Everyone agree? So that means here, this side, if I ran this side over, it would be my y-axis. Does everyone agree with that? And this side of my triangle here would be my x-axis. Does everyone agree with that? Okay? Based on this angle here. This is all that's happening. It's based on that angle. Instead of saying opposite and adjacent, we're now saying x and y. Okay? And the reason we're saying x and y is because we're on a Cartesian plane. We're not just a triangle sitting out in the middle of nowhere anymore, okay? We have coordinates, we have numbers. It's easier to calculate this way. Okay. So now we're just going to set up some ratios. This part is just a reminder of what we just did, so I'm just going to redo it. The reason it's here is so that I can look at it both. So we know that this is y, this is x, and this is r. So based on this angle, all I'm doing is setting up my trig ratios. Sine is opposite over hypotenuse, right? Sine is opposite over hypotenuse. So the opposite is now what? Y. And my hypotenuse is now what? R. Cos is now adjacent over hypotenuse. So it's now x over r. And tan is now opposite over adjacent, so it's y over x. If everybody, once you're done writing this down, looks up on the sideboard right now, right next to the trig reminders, there is a diagram of this and all of the trig ratios set up using x, y, and r. Okay, so they're right there.
Is that r squared equals x squared?
Yeah, so that's when we do Pythagorean theorem. Same thing, yeah, you're just doing using different letters. Okay? And again, it's because we're on a Cartesian plane, so we have coordinates. So as soon as we have coordinates, we need to label them properly as x, y, and then r for radius. Okay, if your original point, px, was in another quadrant, can you figure out what the three trig ratios would be, positive or negative? Remember that the hypotenuse is always positive. Okay, so we know that this is x, this is y, this is negative x, and this is negative y. Does everyone agree? So what I'm going to do is I'm going to show you with one or two of these to show you what happens. So let's say my terminal arm was here, and I created my right angle triangle. Based on my right angle triangle, now, my x is going to be negative. Here, I'm going to actually put this in a different color so that you can tell the difference. My x would be negative. Does everyone agree with that? Because it's on the negative side of the x value. My y would be positive because I'm on the positive side. And my r is always positive. My r is never negative. Okay? Because you're squaring the values. Because think about it, it's hypotenuse, right? A squared plus b squared equals c squared. Well, this is now x squared plus y squared equals r squared, so r is always going to be positive. Okay, so now if I set my trig ratio up here, so sine of theta, anything that uses an x in it will now become what? Negative. So is x used in... So opposite, so this is y over r, so this one's fine. Cos is negative x over r, so this one's negative. And tan is opposite, so y over negative x. So, there is a rule to remember this. Okay, it's called the cast. So what I'm going to do is down here, I'm going to say cast. What the cast rule tells us is based on the quadrant, C-A-S-T, okay? Based on the quadrant, it tells you what trig ratios are positive. If the letter is there, then it means that trig ratio has no negatives in it. Okay, so listen. A stands for all. So in quadrant 1, that makes sense. Every single trig ratio is positive because both x and y are positive. Everyone agree with that? Second ratio is only the sign is positive. Sign is only positive because the rest of them use x, and x is negative in this quadrant. Okay, yeah. Tan. The reason this is because this is x and y are both negative in this quadrant, but tan has both of them in it, so a negative cancels a negative.
Is this what I use?
Yes, wherever the terminal arm is. And then obviously this is cos, okay? And again, this works because based on this quadrant, if you were to set up trig ratios, one or all or some of them are going to be negative, right? Again, this concept looks much harder than it is.
Oh, it's really...
You guys are good? Because I'm seeing blank faces. I'm seeing like, what, Helen? Okay.
I still like all this Greek.
Okay, so let's do an example. Let's do